I think we can start, Nandini.
Hello, Dr. Anjani.
Yes, sir.
Yeah, I think we will start because
Yeah.
I hope, let us hope he joins us soon.
Yeah.
It's, I think it's going to be very early morning there, maybe 6:30 a.m. right now.
Something, yeah. Okay.
Okay, fine. You go ahead.
So, good morning, everyone. Respected Vice Chancellor, Speaker, Deans, HODs, Vice Deans, my dear colleagues and students. I, Dr. Anjani Nagwekar, feeling honored to welcome you all to the international webinar series organized by School of Chemical Sciences, Goa University on two-dimensional semiconductor applications for green energy. This webinar series, having its first talk today, will continue for 5 months, wherein we will be inviting two eminent speakers every month. So today's speaker is Professor David Kahan, who will be soon joining us. He's from Weizmann Institute of Science, who is one of the pioneers in the field of optoelectronics and photovoltaics. The details of the next speakers and talks will be timely communicated to the participants. This event has been in the works for a few weeks, and today we are inaugurating it with the hope that all the participants, especially the research community, will get to make the most of this opportunity by interacting with the top scientists in the field, thus fostering collaborations and remaining updated with the recent research happenings in this field. I hope the talks of this event will also inspire, most importantly, our postgraduate students and motivate them towards research. At the end of every webinar session, we will be sending a feedback link and to the attendees, and e-certificates will be emailed to them after they submit the feedback form. The aim of choosing the 2D semiconductor as a theme of this series is to spotlight the growing significance of these materials due to their emerging applications in energy devices, especially in optoelectronics and photovoltaics. From typical example that we know, which is graphene, the new classes of 2D semiconductors have advanced beyond graphene and now exhibiting remarkable properties and applications. So I hope this series will definitely help the material scientists and researchers to have a glimpse of this emerging area of research. So without taking much time and concluding with this brief introduction, let's begin with this event for today. Thus, I now request our Dean, Professor Nadkarni, to kindly welcome the guests and the audience of today's event. So over to you.
Yeah, thank you, Dr. Anjani. Very good morning to one and all. Honorable Vice Chancellor of Goa University, Professor Menon, who is presiding over this inaugural function. Distinguished speaker of today's event, Professor David Kahan from the Weizmann Institute of Israel. Hope he joins soon. Deans of schools and faculties, Vice Deans of SCS and other schools, heads of departments, principals of affiliated colleges, faculty colleagues, teacher colleagues from colleges, other distinguished invitees from academia and industry, members of organizing committee of this webinar series, and convener Dr. Anjani, and dear students. On behalf of the School of Chemical Sciences of Goa University, it is my pleasure and privilege to welcome you all this fine morning for this inaugural function of the webinar series, Two-Dimensional Semiconductor Applications for Green Energy, the 2D SAGE. This is going to involve, as it was just said by the convener, it's going to involve 2 talks each month from the eminent scientists in this field. We are all aware of the growing global energy crisis, and obviously there is an increasing demand to maximize the use of renewable energy sources and developing energy devices that can generate and store energy. This has become now the need of the hour as well. So we thought that such a platform will inspire and develop opportunities for research aspirants in Goa, as well as this will also result in collaborations through interactions with the key scientists all over the globe as well as within India. We also thought that an event of this stature will help to give prominence and exposure to the School of Chemical Sciences and obviously the Goa University, as we have some of our colleagues who are working in this particular field. So we feel that this will give a proper exposure to SCS and Goa University at national as well as international levels. I once again welcome everyone over here and also take this opportunity to thank our Honorable Vice Chancellor and today's esteemed speakers, as well as the speakers for the future sessions of this series, who in spite of their busy schedules are participating today or are going to participate. Without taking much of your time, once again, a warm welcome to all the participants from the audience for joining us this morning. Professor Professor Verekar, Vice Dean Academic, is going to brief you about the activities at School of Chemical Sciences, so I will not say anything on this. We look forward for such continued support from all of you in future. I wish you very fruitful deliberations and a great day ahead. Thank you. Over to Dr. Anjani.
I now request our Honorable Vice Chancellor, Professor Menon, to give an inaugural address to the audience.
Thank you, Dr. Anjali. Dear colleagues, I hope I am audible.
Yes, sir.
Dear colleagues, resource persons from across the world, students, ladies and gentlemen, a very good morning to all of you. At the outset, let me congratulate School of Chemical Sciences to come out with the idea of having a series of lectures through virtual mode. A webinar on two-dimensional semiconductor applications for green energy, 2D SAGE. Let me say a few words on webinars in general, and then I'll come to the topic of today's interest. In fact, if you see in the past, when the policymakers put their heads together to find ways to increase the gross enrollment ratio in higher education, one of the proposals was to impart education through online mode. However, majority opposed the very idea of online education, citing many reasons. At the outset, let me one among them, or the most important aspect, was India is not acclimatized to classroom, is acclimatized to classroom, face-to-face teaching, hence put a hold on online teaching. Though government was in the process of implementing online on a slow pace, with an idea of implementing this over a period of a decade, the pandemic has made it so fast. In the short span of 1.5 years, it was implemented, which otherwise would have taken a decade or more. Moreover, the UGC's proposal of 40% online henceforth has been warmly welcomed by one and all. Webinars and video conferencing facilitate one-on-one as well as one-to-many virtual meetings between experts and other stakeholders in an efficient way without the need to waste resources or unnecessary travel. Webinars are accessible to a global audience. This means that teaching can reach to anyone across the world effortlessly and conveniently, provided that they have access to the necessary internet and enabled devices. With a solid webinar app, education is no longer limited to only to the campus of higher education institution within geographical reach, but also across borders and oceans. I could see that there are many speakers from Israel through Europe to United States of America for this webinar series. As previously mentioned, webinars are among the most effective digital tools available today. An offline conference would facilitate participants to listen to the speaker for a short duration. However, in the case of a webinar, the recordings are with the participants and can access to the same at their convenient time. In fact, I would say that the initiative of School of Chemical Sciences to begin such webinar is most welcomable approach, as this facilitates young blood in the school to listen to these experts across the world, which otherwise would not have been possible at all. The series surely help in exchanging ideas and offer an outlook on future research directions in semiconductor energy materials from leading scientists or academicians. This would also facilitate them for a continuous interaction through digital media. It's an excellent opportunity to get an exciting overview on specific research topics and might even foster collaborations. Since they are in the initial phase of their career, I would urge each one of you, especially the newly recruits, to make use of this unique opportunity and come out in flying colors so that the name of our university will end of the webinar. Let each one of you get new ideas and let that for a good and vibrant research. All the very best. Thank you.
Hello, Dr. Anjani.
Thank you, Honorable Vice Chancellor, for giving us your valuable time and feedback. We are delighted to have you for this inaugural function. I now request Professor Verekar to brief the audience about the School of Chemical Sciences. So, please.
Thank you, Dr. Anjali. Honorable Vice Chancellor, sir, Dean, Vice Deans, HODs, faculties, and students. Good morning, everybody. I welcome you all for this international webinar series. I'm Professor Verekar, Vice Dean, Academic of School of Chemical Sciences. He is here in front of you to introduce my School of Chemical Sciences to you all. Let me take you to the journey of transformations which our School of Chemical Sciences has undergone. The beginning of the School of Chemical Sciences was, in fact, as a Department of Chemistry of a Center for Postgraduate Instruction and Research known as CPIR. In fact, it was affiliated to then the Bombay University, and it was affiliated way back in 1965. CPIR itself was established under University of Bombay, now Mumbai, in June 1962, soon after the liberation of the Goa from Portuguese in December 1961. After the establishment of Goa University on 1st June 1985, in fact, it's the date when it started, it began. In fact, it was by law enacted 1 year before that, 1984. The Center of Postgraduate Instruction and Research of the University of Mumbai was merged into Goa University. The Department of Chemistry then was finally converted now into School of Chemical Sciences 2 years back. The school is currently located in a new faculty block E. In fact, we moved here in 2013, which has modern infrastructure, which is conducive for quality education and research in chemistry. The school already has the organic, inorganic, physical, and analytical chemistry sections, and recently the biochemistry section has also been added to it. The establishment of the school is in line with the reorganization of the institutional architecture that which will allow us to rebrand and showcase our strength in research as well as in teaching. The research at this school has been recognized by the awards of many projects to the school faculty members from different funding agencies, and also received handsome amounts, grants in fact, from the University Grant Commission, New Delhi, as well as Department of Science and Technology, Government of India, through their prestigious programs like UGC-SAT and DST Feast. The school so far has more than 680 publications and 90 PhD theses to its credit if we count it from 1990 onwards. The students' intake, annual intake for the post-graduation in all these 5 branches which I mentioned just now is 125, while on an average we get 6 to 7 PhD students annually. On an average, 10 to 15 students clear the national eligibility tests such as CSR, NET, JRF, or GATE exams. Our school has 7 to 8 patents either filed or allocated in the last say 15 to 20 years. The school strength, the faculty strength is sanction 1 is around 35, and presently we are 29 in number, and the number is soon going to increase in the coming months. The school faculty has expertise in varied fields. For example, in organic chemistry, many of faculty, they work on organic supramolecular chemistry, artificial photosynthesis, organic solar cells and sensors, synthetic organic chemistry, asymmetric organic catalysis, green chemistry, medicinal chemistry, polymer chemistry, natural product, as well as heterocycles. In inorganic section, the main focus of the research is on materials or solid-state chemistry, catalysis, coordination compounds, synthetic inorganic chemistry, bioinorganic chemistry, nanomaterial synthesis, as well as structural chemistry. While the physical section mostly has expertise in the computational chemistry, electronic structure calculations, materials modeling, advanced computing, reaction kinetics, nanostructural materials, energy and environmental applications, colloidal chemistry, radiation dosimetry, and radiation detectors. In analytical chemistry, which is one of the new sections which we have started some 5-6 years back, has a faculty expertise in the field of process development and optimization, separation and remediation of toxic materials, generation and development of green methodologies, continuous flow chemistry, and the green chemistry. Well, the recently added one, that is biochemistry division, focuses on the research on probiotics, endophytic research, the bioprospecting, bioanalytic chemistry, biodegradation, nanobioremediation, and environmental microbiology. The present strength of the PhD student in the school is around 40, who are engaged in the research on the mentioned topic, which I mentioned topic just now, few minutes back. Well, the school has many sophisticated equipment such as 400 megahertz NMRs, single crystal X-ray diffractometer, vibrating sample magnetometer, atomic force microscope, simultaneous thermal analyzer, SPLC. Besides all the routine equipment like GC, IR, UV visible, and so on. The school attracts many scientists due to its vibrant research culture and the different academic programs of Government of India, such as Inspired Faculty Fellowships, Kotari Fellowship, UGC Faculty Research Recharge Program, Emeritus Professors, etc. Besides this, many of the Western scientists also have come and delivered lectures, as well as they have come on exchange programs in our school some 10 years back. So this process is still continues. Our students, they go to countries like Germany or South Korea for smaller, it's a stint there, as well as their scientists, they come to our school. Well, with this a short introduction, I thank you all for patient hearing, and I welcome you all for this today's webinar. Thank you very much. Over to Dr. Anjali, please.
Thank you, Professor Variker. With this, we end with our formal function. Our speaker, Professor David Kahen, has joined. Welcome, Professor David. I now request Dr. Pranay Moraskar to introduce our chairperson for today's talk, who is our Vice Dean Research, Professor Rajendra Sirsat.
Thank you, Dr. Anjali. It is indeed a pleasure to introduce the chairperson of today's session, Dr. Rajendra N. Sirsat. Dr. R.N. Sirsat is currently a professor of physical chemistry at the School of Chemical Sciences, Goa University, India. His research interest is in the area of theoretical and computational chemistry, focusing on the applications of molecular electrostatic potential. He works in the field of chemistry education as well. Professor Sirsat received his master's in physical chemistry and subsequently PhD in chemistry from the Department of Chemistry, Pune University, India during 1989 to 1994. Professor Sirsat has published several high-impact research papers in international journals and has also co-authored a book entitled Electrostatics of Atoms and Molecules. Professor Sirsat has also served as a visiting researcher at the Jackson State University, USA during 1999 to 2001 and at the University of Kiel, Germany during 2005. I would like to mention here that Professor Shirsad is a very popular teacher in Goa, and his lectures on quantum chemistry and group theory are very much liked by his students. Therefore, he has been a regular invited guest speaker and a teacher across colleges and universities in several states of India. I now request Professor Shirsad to introduce our today's guest speaker of this webinar and also chair this session. Over to you, sir.
Thank you, Pranay. Am I audible?
Yes, sir.
Okay. Thank you, Anjani and Pranay, for giving me this opportunity. Good morning, everyone. I'm happy to introduce our today's speaker, the first speaker in this series, very eminent and senior scientist, Dr. David Kahan. He is a professor at the Department of Materials at the Weizmann Institute of Science in Israel. And since 2017, he also heads the research group at Bar-Ilan University. He studied chemistry and physics at Harbin University of Jerusalem, studied materials and research at Northwestern University, USA, and conducted his postdoctoral research in biophysics of photosynthesis at Harbin University. And at the Weizmann Institute, where he started his work on solar cells. As Weizmann Fellow faculty, he specializes in optobioelectronic material chemistry and physics, and focuses now on what can make such a material sustainable, and he is significantly contributing to the field of photovoltaics these days. Professor Kahan has published large number of papers, and he has more than 25 patents to his credit. Professor Kahan has chaired various scientific advisory boards. He has been a member of various Israel's scientific advisory committees and has received numerous prestigious national and international awards and prizes. For his outstanding achievements and contribution to his field of research, he is recognized as a Fellow of American Vacuum Society, Materials Research Society, and Helmholtz International Fellow. He is visiting professor at various universities, including University of Cambridge, Princeton University. He is presently a visiting professor at Chiba University, Japan, Center for Nanoscience and Engineering at IISc Bangalore, and is active in the energy and sustainability education and science for peace. Okay, so I hand over to Anjani, and I welcome Professor Kahan for this seminar. Please take over, Anjani. Thank you.
Thank you. I hope you can see my screen.
Yes, no, sir. Yes.
It's okay?
Yes.
Okay. Thank you very much. Thank the organizers for this opportunity to give this lecture somewhat early in the morning for me, especially considering that last night between 8 and 9 o'clock in the evening here, I gave a lecture to the American Vacuum Society in the United States. But these are the miracles of being able to give lectures even without being there, something that we deplore in this time, but it also has its advantages. The connection between 2D materials and my lecture will only become clear at the very end, when I will give some views that have to do with the egos and prizes of scientists with respect to halide perovskites. Because the halide perovskites were of interest in research for over 2 decades because of their two-dimensional properties and the fact that they showed quantum confinement. Something that's forgotten these days because of all the interest and noise around their ability to make remarkable devices. But first, I'll give you some view of something I learned from Professor Helmut Ringsdorf, a polymer scientist from the Max Planck Institute for Polymer Science, who used to frequently come to Israel and asked to talk to Israeli students to try to impress on them that being a brilliant scientist, if you succeed in that, that is not enough. And he gave some examples, and that was my inspiration for this talk, which I was asked to give some time back in Berlin. I'll start with something very local, and that has to do with the fact that after the Second World War, 1 year after India, the State of Israel was created. And one can say it rose out of the ashes of the Holocaust that happened in Europe, and which was which threw a big shadow over any relations between the new State of Israel and Germany. 12 years later, this historic meeting took place during the United Nations General Assembly, when David Ben-Gurion, the first Prime Minister of Israel, went down from his 30th floor, from his 40th floor room to meet Konrad Adenauer, who was staying 5 floors below, which was the first meeting between two high-level Israeli politicians, and it had a background. But first, 5 years later, official diplomatic relations were established between Germany and Israel, which was a very major happening, accompanied by riots in Israel because of protest. How could this happen? It had to do with scientists. In the mid-50s, 3 scientists, 2 Israelis, and 1 German made contact. It started with 2 Israelis, 2 scientists, high-energy physicists, Gentner and de Shalit, joined by another Israeli, and they found common language in science. And those scientific relations were the basis for what later became the diplomatic relations. The first official German delegation to Israel is photographed here at the airport in Zurich. It was a delegation of the Max Planck Gesellschaft that came to Israel in 1959. And it had, among them, the then head of the Max Planck Society, Otto Hahn. I give this as an example of how science can be a bridge between nations. Now we'll look a little bit more into Otto Hahn. You probably know that Hahn and Lise Meitner, Otto Hahn the chemist, Lise Meitner the physicist, together led the basis for what became our understanding of nuclear fission. They worked together for many, many years, where it was clear that it was at least an equal partnership. Lise Meitner was an Austrian who was baptized as a child and came to Germany to work in what was then one of the best research institutes in the world, the Kaiser Wilhelm Institute, which nowadays are Max Planck Institutes in Berlin, where she worked with Hahn under the restrictions of a woman being a woman scientist at that time. She established herself as a great authority. And here is a picture of Lise Meitner with Max von Laue, whom we know from crystallography, the basis of crystallography, and Dirk Koster, whom you do not know. He was a Dutch scientist, but he played a major role together with Max von Laue to get her out of Germany when her time had run out in 1938. This is her in the 30s. Otto Hahn, working with Fritz Strassmann in a brilliant chemical effort,
Excuse me, sir.
showed
Excuse
that
me,
under
sir.
certain conditions, hello, showed that under,
Excuse me. There's some noise coming.
pardon?
There's some noise is coming.
I cannot hear you.
Some noise is coming during your talk.
There is a noise.
Yeah, there is a noise.
My room is completely silent.
Anjani, is it for you also?
No, Professor. Yeah, there is some noise we can hear, but we tried at our end. The issue is not here. I think. Maybe. Okay, let's continue.
I have no idea how to take care of that. Yesterday I gave my talk via Zoom with the same system and there was no such problem. So I'm not sure what I can do about it from my side. Do you have any idea?
Some loose contact somewhere.
Before starting my lecture, I did check that the Google Meeting program gives, and it seemed okay. So I'm not sure what I can do about it.
Anyway,
So is it very difficult to understand me? Hello?
Yes, Professor. You can continue.
It's very difficult to understand. Hello?
Hello. Yeah. You can hear.
I'm asking if it is difficult to understand what I am saying.
sir, it comes only when you speak. It comes only when you speak. Otherwise, it is not there.
Only when I speak.
It is better. It is better now.
Now it is better. Yeah. You can continue. Yeah. Okay.
Okay? Let's hope for the best. So Fritz Strassmann with Otto Hahn did an experiment where they found to their great surprise that when they bombarded uranium with neutrons, they found barium. The news about that reached Lise Meitner, who had been smuggled out of Germany by Dirk Koster and had reached Sweden, where she was initially hiding, and then she went to Denmark to meet her nephew Otto Frisch. And the two of them figured out the concept of nuclear fission. And we know the rest. As you know, only Otto Hahn was recognized by the Nobel Committee. Lise Meitner was not. The reasons for that have been discussed at length once the Nobel archives were opened, and supposedly had to do with a fight between the chemistry and physics chambers of the Royal Swedish Academy. Hahn continued to work during the Nazi regime. Meitner re-established relations with him after initially writing a furious letter about his behavior, but never sending it. It was found in her estate. Here she's seen with Hahn and Max von Laue. This is not the end of the story of Lise Meitner. Here you see her as the only woman in a high-level meeting in 1920 in Berlin-Dahlem, here in Copenhagen, one of the famous Solvay meetings together with Irene Joliot. It must have been pretty lonely there. By the way, this meeting was held already after the ascent of Nazis in Germany. But there's another story here. You probably know of the Auger effect. And the Auger effect is named after Pierre Auger. He did his PhD studies in the area of emission of electrons and found the effect and published it in 1923. Much less known is that Lise Meitner found the effect and published it in 1922 and 2 papers. It was a side effect of her main research, but there is no question that she found and published the effect first. But no one talks about the Meitner-Auger effect. That is the credit problem that we have, even if priority is established. But it goes back much further. Here are 2 gentlemen from the 17th and 18th century in England. One was the city architect of London, the other master of the Royal Mint. They came from very different social background. There's a third one, Germany. Talented, as were the other 2. And this is Leibniz, Robert Hooke, and Isaac Newton. Leibniz and Newton independently invented calculus. Especially Newton was not happy about sharing credit. That is even clearer when you look at his relations with Robert Hooke, who rose from rather low social status to fame. Hooke was president of the Royal Society. He definitely had a lot to do with F equals ma, Newton's first law, and the understanding of light. Newton, as president of the Royal Society after Hooke, was very thorough in trying to get rid of anything that might remember people of Robert Hooke. As a result, the portrait that I show you of Robert Hooke may be him, we don't know, because we do not have a picture of Robert Hooke that we are sure is him, as whatever was there in the Royal Society disappeared. So there's no question that Newton was a great, great genius. That doesn't mean he was a nice person. We'll go on to the discovery of oxygen. This is such a nice story that even the play has been written about it by Roald Hoffmann and Carl Djerassi. Roald Hoffmann, a Nobel Prize winner for frontier orbitals, and also the Hoffmann of the Woodman-Hoffmann rules, and Carl Djerassi, the father of the contraceptive, someone who should have gotten that prize but never did. You can find it on the web. So, an alchemist who preceded all the major actors, Semivogius, was the first to notice that there was a substance in air that was more active towards fire than the rest. And then we have the 3 principles that also appear in the play: Scheele, Priestley, and Lavoisier. Scheele was a pharmacist in Sweden, and he discovered what he called fire air. Priestley, an English experimenter, found what called dephlogisticated air. They both shared their findings with Lavoisier, Antoine Lavoisier, when in writing and when by visiting. There is no question that Lavoisier improved a lot on what he learned from these two. But there was also, according to the story, his wife, Marianne Polze, who was very careful to do everything to make sure that her husband and only him would give credit for the discovery of oxygen. This is what happened, and maybe with some justification, but the other two should at least get shared credit. And naturally, we know Lavoisier as one of the fathers of modern chemistry, and that no one can take away from him. But this picture shows that the end of Lavoisier, who was too much connected with the old regime in France during the reign of terror after the French Revolution, was guillotined. We get now to a very interesting story, and that has to do with evolution. This person was a kind of adventurer, Alfred Russel Wallace, an American. And he was very much interested in the animals around Indonesia and Malaysia. Then there was Charles Darwin. Charles Darwin of the Beagle, the ship that went around the world, or nearly around the world, and who is considered the father of modern evolution, which he put in writing under great pressure of his friends in the book The Origin of Species. Why the pressure? Because they had learned that Wallace had reached similar conclusions and was publishing. Here there was again a big gap in social status between Wallace and Darwin. And Wallace knew, and Wallace, in some ways, here he is again, adored, admired Darwin. There was never a question of him feeling that Darwin had taken his credit, because he viewed Darwin probably as much more deep in understanding the implications of survival of the fittest, which is a central theme for evolution. Actually, Darwin, to some extent, at the end of the life of Wallace, supported him financially. There's another person we'll come to in a minute, Jean-Baptiste Lamarck, because Lamarck is the one that we are taught, at least in high school, of the person who said that if you change the environment of the animal, of the organism, often enough, then the organism will adapt. And his example was the tail of the toad, which we know is not correct. Although modern epigenetics suggests that it's not completely wrong. Lamarck comes back in this very sorry story. There are a few cases where we have scientists, in hindsight, we look at them and we see that they knew the answer to the question they asked when they were doing the experiments. That is naturally a far cry from the way that we teach students that science is being done. You're supposed to be the objective observer. You design the experiments to get closer to the truth without prejudice. Well, there are two examples, one rather famous, the other one which I present here as a possibility, that suggests that these people, Gregor Mendel and Walter Shockley, knew the answer, and they were right. So we're geniuses. Mendel, in his experiments with peas, in order to look at genetics, how traits are inherited, and Walter Schottky of the Schottky barrier did experiments with what we know nowadays is a near impossible material to get nice reproducible results, copper oxide. But the concept that he was after to prove is correct, and it's one of the pillars of modern electronics. But if you're wrong, it can be catastrophic. And the famous example is that of Trofim Lysenko. Lysenko was a Soviet geneticist, agricultural geneticist. And he was a strong Lamarckian, say, although it's not fair to Lamarck because Lamarck did many things in his career, and the one about which he is famous or infamous is only a sport. Lysenko claimed that if you took a certain type of wheat, you could actually find conditions by pruning it to give you 2 harvests a year instead of only 1. And he produced data that supposedly were correct. Supposedly. He became a darling of the Russian establishment. Here is he studying, and here is Lysenko giving a talk. And it was in 1935. And his conclusions were adopted by the regime, which led to terrible hunger because of failed harvests year after year. And that was an example of a very bad abuse of science, because the idea behind the scientific experiment was to a great extent something we connected with the dogmas of community. And that combination, or anything like that, was not there with Mendel or Schottky. It shows you how dangerous it is to mix religion and science. Why do I dare to say religion? Because in some ways, communism is a religion. Now, another example of that being a genius does not mean that you have to be a very nice, a good or honest person. One of the great scientists in the 20th century is William Bill Shockley. He's shown here with John Bardeen and Walter Brattain on this PR picture of Bell Laboratories, of the first transistor, which was built by Walter Brattain and conceived by John Bardeen. Schottky was their boss. And it was very hard for him to swallow that these two guys that worked under him had beaten him to get the first transistor. It was the point contact transistor. He developed during a few days the junction transistor, at least the idea for it. As a result, the three of them shared the Nobel Prize, but no love was lost between them. Bardeen left Bell Labs, and Brattain asked the management to make sure that he would never again have to work close to Shockley. Shockley also was the person who brought electronics to Silicon Valley. even though there was Hewlett Packard before. His which then became later Fairchild, from which came Intel, were the main driving force for Silicon Valley. But there's more that has to be known about Shockley. Shockley, after failing in business, if you could call it that, went to Stanford University as a distinguished professor. And when I was there at Stanford, he was teaching a course which was called the Dysgenic Question, New Research Methodology on Human Behavior, Genetics, and Racial Difference. And what is dysgenics? It's retrogressive evolution through the disproportionate reproduction of the genetically disadvantaged. I don't know if you figured out what he was teaching. He was teaching a course about the inferiority of one race over the other. And you can guess which on which. And he was so smart that he used academic freedom that Stanford University could not stop him. Another famous case of credit, which brings us also to the issue of being a nice or not so nice person. This is the famous photo 51 that all of you have to know. But it's also a story of Mr. Jim. Because here are three people: Rosalind Franklin, Jim Watson, and Francis Crick. Rosalind Franklin worked in London with Maurice Wilkins. She was told with, and then she found out under, produced this first brilliant picture, X-ray diffraction picture of DNA. It shows for anyone who delves into the math of diffraction indisputably that it's an helix. Actually, two helices. She was a very methodological worker. She got this picture with one of her students, was very happy, but went on to finish an earlier project. And unbeknownst to her, via Maurice Wilkins and his friend, the head of the lab in Cambridge, this picture reached Watson and Crick, who were trying to, just as she was, and many others, among them Linus Pauling, to understand, to find out what is the structure of DNA. So they used this picture without her permission, without her knowing. Afterwards, there was the book of Watson, in which he made fun, in a not so pleasant manner, of Rosalind Franklin. Rosalind Franklin died of cancer in the late 50s before Wilkins, Watson, and Crick got the Nobel Prize. Jim Watson, who's alive still today, is a fervent supporter of eugenics. By breeding humans in a controlled manner, you will be able to improve the human race. Eugenics is not something that is accepted today, but it has taken a long time for the scientific community to essentially disavow Jim Watson, who indisputably is a brilliant scientist, as is Francis Crick. One can go to extremes, and this is an extreme example. That is the example of two famous German scientists from the beginning of the 20th century, first half of the 20th century, Johannes Stark and Philipp Lenard. They're two physicists. They both got Nobel Prizes. Philipp Lenard for cathode ray tubes, the cathode rays, and Johannes Stark for the Stark effect and further work, which is the effect of a strong electric field on energy levels. There was mutual admiration between Stark. No, not mutual. There was admiration from the side of Stark for the young Einstein, because he invited Einstein very early on to write a big article for an encyclopedia of physics on relativity. But these two became fervent Nazis. So fervent that they joined the movement of cleaning physics from contributions of Jews, which led to this series of 3 books, German Physics. Physics clean of influences by Jews, so that none of Einstein's work and of many others appeared there. There, I would say, at the very, very extreme of what your political opinions can do about your science. In other words, you will change the science so as to make it fit to your political opinions. On the other side of the slide is a picture that shows something completely different. Here are 5 people with excellent relations between them. Einstein, Ehrenfest, De Sitter, Lorentz, and Eddington. Lorentz was a kind of the mentor of Albert Einstein. Ehrenfest took the chair in physics in Leiden when Einstein said thank you, and was a famous physicist by himself, but also a very tragic person. He committed suicide in the end. De Sitter was a Dutch astronomer, and Arthur Eddington, we'll come to now, an English astronomer. Here they're shown at the picture in Leiden, the Netherlands. What you have to know about Arthur Eddington is that he came from a family of Quakers. Quakers was the group of people, some of whom fled to the United States, the new territories from England, because they were not very well tolerated. They were anti-violence, in principle, pacifists. Einstein was a pacifist. He made one exception, which was the Nazism. So now we go back to the First World War for a combination between science and politics. In October 1914, just after the beginning of the First World War, a group of German intellectuals, 95, published a manifest, which was in a way a much lesser known manifest that was published by English scientists. So it's not one-sided. And in this manifest, they defended Germans' right to war. And that anything bad that is said about it is not true. As ist nicht wahr. It is not true. At that time, Germany was in some state of mass psychosis. Everyone was in favor of the war, except Einstein. 2 people refused to sign this manifest, Einstein and one person from the theater world. But Haber and Planck signed. Willstatter, Röntgen, Ostwald, Nernst, the fathers of physical chemistry, Wien of the Wien law, Fischer, the organic chemist, they all signed. Laue did not sign. He did not say, I don't want to sign. He just kept quiet. Here we see Einstein with his friend, Fritz Haber. Fritz Haber who was a person that was both brilliant and tragic. It is not an exaggeration to say that today we live because of Fritz Haber. Because Haber, together with Bosch, the chemical engineer, established the Haber-Bosch process. He discovered it in the laboratory in Karlsruhe to fix nitrogen. And without fixing nitrogen, we would not have modern agriculture. So we owe him a lot. But he is also the father of gas warfare, something in which he took personal interest, traveling to the front in order to check out the efficiency of the means that were developed under his guidance. Einstein, all through the First World War in Berlin, kept to his pacifism, notwithstanding the enormous external social pressure. You will know the story. In 1916, Einstein completed his general theory of relativity, which very clearly, already in its earlier phases, 1913, it was realized that it could be checked experimentally by checking the position of stars during a total solar eclipse. Actually, in 1914, a mission was planned going to the Crimean Peninsula, but it never took place because of the First World War. And that was good news for Einstein, because at that point, his theory was not sufficiently different in terms of the outcome from classical Newtonian understanding to have shown a significant effect. Sorry. The situation was different when the theory was completed in 1916-17, and it became clear that the next eclipse would be a brilliant opportunity to check this. Now realize, Germany was at war. Berlin was in Germany, and that's where Einstein was, and that's where Einstein published his papers, which were then transferred by the Dutch astronomer De Sitter to England. De Sitter appeared in a previous picture. In England, they reached one of their preeminent astronomers, Arthur Eddington. And now the incredible, at least for me. The First World War was still raging, and Arthur Eddington convinced the Royal Society to fund the experiment to check Einstein's theory, while all of Britain was one big block of anti-Germanism. And Einstein was considered a German. And he succeeded. There were two missions, one sent to Brazil, the other to the west coast of Africa. And when the results came out, it was clear that the result was much closer to Einstein's prediction than to that of classical physics. So it was undoubtedly, in my mind, the fact that there was a very clear separation between the politics and the science, as was the case for Einstein, that made this incredible collaboration happening. And naturally, you know the famous story that Einstein was asked, what will you do when the experiment shows that you're wrong? And he says, well, when I'm wrong, that's at least one version. Then the French will say I'm a German scientist, and the Germans will say I'm a Jew when I'm right. And the French will say I'm a great man of the world, and the Germans will celebrate the German scientist. Just before his death, Einstein signed a manifesto that was drawn up by Bertrand Russell, which was essentially a call to the arms, to the disarms, to world peace, because of the fear of the atomic age. This led indirectly to a series of conferences that still goes on. Pugwash conferences, funded by a Canadian millionaire originally, and they brought together at the height of the Cold War scientists from the West and the East, from China, Russia, Europe, and the United States. It was always thought, at least by me, that it didn't do much good until the archives of the Kremlin were opened, and it was found that not once the political leadership in the Soviet Union had turned to scientists who had been pre-selected, naturally, by the Soviets to go to the Pugwash conference to ask them how to interpret certain behavior of the Western nations that could easily be misinterpreted as direct threats to the Soviet Union. And in that way, even Brezhnev was stopped from taking action that would have been disastrous for the world. There's one person here who I want to single out, and it's Linus Pauling. Linus Pauling got the Nobel Prize for Chemistry, because he's one of the fathers of modern chemistry. There were two more scientists that got him, Andrei Sakharov, the father of the hydrogen bomb in the Soviet Union, and Joseph Rotblat for the Pugwash meetings. Both Rotblat and Pauling co-signed the Russell-Einstein Manifesto. There's another thing to Pauling. Let's go back. Sorry, because I should have arranged that, but yeah. Pauling was also in the race for understanding DNA. And Pauling was a brilliant crystallographer. But he could not go to England because the US at the time was in McCarthyism time, and his passport was taken away because he was a dangerous communist as a pacifist. Because I forgot to tell you, Pauling, like Einstein, was a convinced pacifist. So he couldn't go, and he sent his son, Peter Pauling, a very intelligent person, but not his dad. And there are quite a few people who think that if Linus Pauling had come, visited London, and seen the picture, he would not have come up with turned out to be the wrong model for DNA, and would have beaten Watson and Crick to it. That's another example of how politics can interfere with science. And I was asked to add something about halide perovskites. Well, I didn't quite know what to do, and then something fell in my lap which allows me to do that. Because we talked also about egos and prizes. So here are the principal actors, as far as I can see, some of whom may not be that well known to you. Dieter Weber was the first to make an organic-inorganic halide perovskite in the late 70s. Then in the 80s, he showed that there was lattice dynamics because of the organic cation. David Mitzi, in the 90s and early 2000s at IBM, pursued their study, finding ways to prepare them and also being able to make transistors out of them. He was the second to cope light emission out of them. The first one was a Japanese paper in 1994. Then was Mercouri Karasidis, who in 2012 published the first paper on the material with a solid-state solar cells. But there are these three Japanese that I will focus on. Kajiro Tsushima, Akihiro Kojima, and Tomiyasaki. Because they are three of the four co-authors of a seminal paper that preceded Canazidis on a dye-sensitized like solar cells with electrons. And we'll come to that. And then there's Namie Park, Henry Snaith, Michael Gretzel, Samuel Self, and Michael Lee. Namie Park followed up on the work of Miyasaka and made a solid state, what he thought was dye-sensitized cell. Henry Snaith with Michael Lee, and Michael Gretzel and Sang-Il Sok and their groups all simultaneously came up with remarkably, for that time, remarkably high efficient solid state solar cells. This is the 2012 paper of Henry and his group, which has Tom Miyasaka and his co-worker Murakami and Michael Lee, who went to Miyasaka to learn the tricks of the trade. It was submitted the 31st of May 2012. This is the paper of Michael Gretzel and Namie Park, because that's where Michael and his group learned the tricks of the trade. It was submitted a month later, but published before. And there's a big story about it, and I do not know if it's true or not. And then there's Sang-Il Sok, who sent this paper to Nature Photonics, and it apparently went through a lot of problems with the reviewers. It was published just 2 weeks after that of Michael, and 1.5 months after that of after that of Henry. But it came out only in June 2013. Now they have stars here. The people with the stars recently got the big prize, the Bank Prize for devices, the UK prize. So back to prizes. You see, some of them didn't get it. And that's very interesting. So why did he get the prize? Because Namie Park was there very early on. In 2011, he made a 6.5% quantum dot sensitized solar cell, and that came after, before Mercury Canazidis. In 2012, in Nature was a dye-sensitized solid state cell with high efficiency. So why is Park there and not Mercury? But in 2006, we're going back quite a bit, at an ECS meeting in the US, Kojima, Tsushima, Miyasaki, and Shirai first reported on their new photoelectrochemical cell with lead halide compounds, with halide perovskites. Shirai, it is now understood, also from my research and that of others, that he was a very senior person of a big Japanese project on 2D halide perovskites. And he was there as a senior scientist, but did not contribute very much. But we have Miyasaka, who got the prize, Kojima, who got the prize, and Teshima, who didn't get the prize. How does that work out? There's no question that all these people are very deserving. They helped in creating a revolution. But I'm a little bit worried about this person. I don't know the person. I also don't know Akihiro. I only know Tom Miyasaka. In my mind, there's no question that he is one of the most central figures in this whole group, together with Dieter Weber. So they published in 2009 their work, which was first reported in 2006 in JACS. In 2019, Tom published the chemical reviews on halide perovskites, his view. And here he writes the story, which is corroborated by another source. Kojima was a grad student at Tokyo Polytech, and he came to Miyasaka's lab to learn to work with dye-sensitized solar cells through a collaboration between that university and the university where Tom Miyasaka was. And then there's written, the collaboration was initiated by Dr. Kenjiro Tsushima, who was Kojima's mentor. And later he worked in a company that Miyasaka founded, which still exists. The work was also an extension of studies being done by Teshima and Kojima, where Teshima was the mentor and Kojima was the student at Tokyo Polytech, with respect to the quantum photochemistry of halide perovskites, because they were studied, as I told you at the beginning, as 2D materials with quantum confinement effects. And that's because there was a big project going on in Japan. And Tom Miyasaka himself concludes it was Miyasaka's encounter with Teshima that triggered the start of the perovskite photovoltaics. So I leave you with that. I hope I gave you some food for thoughts on scientists, their egos and prices. How sometimes egos or politics can interfere with the way we do science. And I urge you not to go that way. And yes, if you miss a prize, it's a nasty, not pleasant feeling, but be aware, you're not the only one. Thank you.
Thank you, Professor David. I'm audible?
Yes, yes.
Okay. Thank you, Professor David, for nice informative talk, which actually tells a journey of science, a lot of historical events, interference of politics in science, and a development of solar cells, even though there are problems. I will request audience if there are some questions to Professor David. Yes. Yes, Dalila?
Yes,
Yes.
yes, Professor. I had a question. I wanted to know how can we prevent the retraction of papers from eminent peer-reviewed journals?
How can you what?
How can we prevent the retraction of papers from peer-reviewed journals?
Oh, that is very difficult because the peer review process is flawed because it's done by humans. And we all have our schedules. You're not always thorough. So I view retraction as a positive thing. It means that the system can self-regulate. I was involved in one case where we were working in a field and a very important paper was retracted because one figure had data that could not be reproduced. But all the rest was found to be valid. However, the journal said once one part of a paper is incorrect, the whole paper ceases to exist. I found that problematic for science, but that is at the moment the rule. If you are worried about rejections of papers, we are in a field that compared to, for example, the study of stem cells, is in very good shape. There are fields where retractions are much more common. The fact that eminent scientists publish, and that is then the answer I can give you, should make you more aware of possible flaws in the paper. In other words, you definitely should look for the big name effect. You cannot stop it because they will have an advantage in the peer review. That is, I think, any journal that is willing to be honest will have to agree to that. However, as reader and as scientist, you can be careful, more careful with such a paper than with one of people who have a less big name. That's the only advice I can give you.
Thank you, Professor.
Diksha, you can go ahead, Diksha. Diksha is having a question. Yes.
Hello, Professor. So, Professor, I had one question with regards to solar cell. Silicon solar cells have estimated a lifespan about 20 years. So, can we guarantee such a lifespan by using peroxides?
At the moment, not. At the moment, not, because of what we know about the problems with making a system that is multi-layer with many components that all have to fit, that should not react with each other, and that should be protected from the environment. The protection from the environment is possible. We have proven this in other cases where devices can be encapsulated and protected for 20 years. But the presence within that encapsulation of many components is at the moment something that poses a problem. And at the interfaces, you will get processes that have to be prevented in order to get to a 20-year lifespan. So at the moment, the answer is no. Is it impossible? No, it's possible. Will it be worth it when we find out how it is possible? That's another question.
Thank you, Professor.
Dr. Pranay Moraskar has a question. Yes, Pranay, go ahead. Pranay, can you hear me? You have raised the hand. If you have a question, please go ahead. Yes, I think, yes. Pranay, please go ahead. Hello? You are not audible. Someone else? Yes, I think there is some problem with Pranay. He wanted to ask questions. Someone else has a question, please go ahead. Yes. Okay, Pranay, please. Pranay, you have some problem in asking?
Yeah, hello. Can you hear me, sir?
Yes, we can hear.
Yeah,
Please go
there
ahead.
was some network issue.
Okay, go ahead.
Mr. Khan, I have one question here regarding the current energy crisis scenarios. The world wants to move from fossil fuels to, let's say, cleaner sources of energy, and whether it is nuclear, solar, or other green hydrogen sources. But for a country, developing country like India, we definitely have a lot of sun, and we would like to work in solar energy to achieve our clean energy goals. But we are still heavily dependent on imports of fossil fuels or other nuclear energy sources. So how do you look at this scenario for a developing country like India and the politics of it? How are we supposed to grow towards a clean energy sector while continue to use our carbon-rich coal deposits?
The challenge that you face is enormous, I agree, but it has been there enormous for a long time. And your country, like many others, has done very little except lip service and what is called greenwashing. Therefore, the fact that it's a big challenge doesn't mean you have to work on it. It will go, it will not happen at once. It can be done over a period of a decade, but it has to be done with political will. At the moment, in countries like India, and unfortunately my own, that political will is lacking. So we do as if we go to Glasgow and we rub shoulders with the great of the earth, or are ourselves the great of the earth. But when we go home, and India is not the worst example.
All right. Thank you,
In
Professor.
the case of Australia, it's much worse. Australia doesn't have all of the problems of India.
Sure.
But the state of Victoria refuses to stop burning brown coal. So what India can do is to invest for the interim period in the chemical industry that can, in a centralized fashion, convert coal to less polluting fuel, while having a central way to store the CO2 so as not to add it to the atmosphere. In this way, India, not now, but 10 years from now, would be able to be a leader in decarbonization and be able to create a new industry that would bring it a lot of wealth. However, what it requires is political will now. This or any other approach. You can start with encouraging your local solar panel industry, your solar heater industries, and give tax breaks for people who will put panels and heaters on their roofs. Industries that will do that. All of these things are possible. Making good solar cells today is not rocket science. The government gives lots of subsidies. The way that they have been behaving towards cleaner energy sources has been one of what I call doing as if. And it's not, India is not alone. Just because you're a lot of people, the problem is many times bigger than in most other places. But it depends on you and your students and your peers to make your voice heard and to try to convince the population the fact that it is difficult doesn't mean it's impossible.
Professor, just an extension of this question, if we are to extend towards solar energy conversion via photovoltaics and achieve the energy needs, do you believe that somewhere down the line, due to extensive commercialization, managing the electronic waste due to these solar cells will be a challenge? Or what steps?
It is already now a challenge, and there are ways to do it. But you could, for example, I know that you have a photovoltaic industry. Let's assume that there will be a renewal of that industry. If the solar panels coming from India would be designed from the beginning so that they are fit for end-of-life disposal and recycling, which is not the case what we have now with any of our solar panels, then that would be a huge step forward. Because solar panels are among the easier electronic devices to dispose of and recycle. Your smartphone is much more difficult.
Okay. Yeah. Thank you,
So
Professor.
it is a matter of where it can be put into the design so that, and that is what is happening at the moment in certain rich West European countries, so that the end of life, this assembly and recycling will be that much simpler, more effective, and less energy consuming.
Okay, thank you. Thank you, Professor.
Can I ask a question to Professor David? Dr.
Yes,
Nandakumar Kamath here.
Yes, Dr. Kamath, please.
Professor David, my question is very specific. What is the present constraint on using gallium arsenide based cells, which are more efficient in absorbing higher energy photons? The reason is I am asking is we have vast deposits of aluminiferous bauxite in which we have not extracted India. Millions of tons of gallium is readily available for extraction. And India can intelligently make use of this gallium, which is locked up in the bauxite or lateritic deposits. It is extractable. But I think there is some limit on use of the efficiency because of the efficiency of these gallium arsenide based solar cells. What is the constraint and what is the future of improvement of gallium arsenide based the solar photovoltaic cells according to you?
We need a cheaper method to make the gallium arsenide epitaxial film, because the high efficiencies come from cells that use high quality epitaxial film. So at the moment, the processes that they have, MBE and MOCVD, are too expensive. So if a cheaper process can be developed, it will become much more attractive. You will then be stuck with the problem of arsenic, which is an environmental problem that will have to be dealt with by design upfront of being able to recycle it the way that First Solar claims it can do with cadmium telluride, with the tellurium and with the cadmium and cadmium telluride. But I see as the main problem for large-scale use, assuming you can take care of the environmental issues and the recycling issues, that the way that there has to be found first a low energy, reliable way to make high quality epifilms. And we don't have that at the moment.
Thank you, Professor.
Okay, thank you, Professor David, for your interaction with our teachers and scientists and the students. I give my mic over to Anjali now. Thank you, Anjali.
Thank you, Professor Shirsai.
Okay.
Once again, thank you so much, Professor David, for accepting our invitation. We were really delighted to have you as our first speaker today. I also thank now our Vice Chancellor, Dean, Vice Deans for their support for this event, and also thank our organizing team, Dr. Pranay, Dr. Diktesh, Mr. Vishnu, Dr. Sandesh, Dr. Vivekanand for their cooperation. And finally, I thank all the participants for joining and making today's event a success. The feedback link is shared, so you can please fill it and have your e-certificate. See you all for the next talk, the details of which we will be communicated to you. Thank you, Professor David.
Thank you.
Yeah, see you.
Bye-bye.